Right, good morning. So welcome to the seminar, Modeling Social Complexity for Public Policy by Associate Professor Michael Lee. Michael is good. Right. And my name is Wentung. So I'm chairing this session. Right. And Mike is actually not really a stranger to NTU. Right. So he was with NTU for 5 years. Before joining University of Amsterdam in 2013. Yeah. So afterwards, Mike actually maintains very close relationship with NTU through collaboration with Complexity Institute, right? And Mike is currently an associate professor at the University of Amsterdam, where he leads the Computational Science Laboratory in the Informatics Institute. So he's also a principal investigator for complex systems at the University of Amsterdam Institute of Advanced Study. And this event is co-organized by School of Computer Science and Engineering and NTU Institute of Science and Technology for Humanity, so NIST for short. So NIST aims to address social challenges through interdisciplinary collaboration between STEM and non-STEM experts. So STEM, so that stands for science, technology, engineering, and mathematics. So in this talk, so Mike will explain and demonstrate ways in which complex systems models can be applied to reason about social systems and how these models can be used to reason about policy. And before I pass the floor to Mike, right, and I'd like to remind audience, right, so you can ask questions anytime by type your question in the chat box. Now, Mike.
Okay, thank you very much, Wentung. I guess everyone online can hear me. If you can't, just shout. So thank you very much for letting me talk here today. I'm very happy to be here. As Wentung said, I spend my time officially 2 days a week at the Institute for Informatics and 3 days a week at the Institute for Advanced Study, which is kind of an interdisciplinary center in the middle of Amsterdam that tries to connect all the faculties together. So I think there's a little bit in common with what's going on at the Institute here and what we're trying to do, particularly looking at the application of what we call in Dutch the beta and alpha sciences, or beta and gamma, the hard sciences and the soft sciences. And that's where my research over the last 10 years, let's say, has really started to evolve. And my kind of approach is using a complex systems approach, let's say. And I want to explain in the first part of the talk what I mean by that, and also how that's useful particularly for social systems. And then I'll talk about one project that we have at the Institute for Advanced Study on trying to model and understand school segregation. So I'll explain what that is as well. So first, a little bit about complexity. So if you're not familiar with the term complexity, complex systems are systems which contain sets of elements, let's say collections of individuals, or can be collections of particles. And those individual elements have relatively simple rules by which they behave. But when you put these particles or these individuals together, you start to get strange phenomena or emergent phenomena, things that you might not expect to happen. These have been found all over the place. People in physics study them, people in sociology study them, people in finance study them. And at the core, what you're trying to understand is, for example, why people like this, right? So traders who are usually behaving in ways that they think is rational and they want to maximize money, but they all operate together, and through their interaction, they lead to phenomena like this, where you get crashes. None of these individual traders want the crash to happen, but it happens anyway. Or why you have people like this who are trying to drive very sensibly, but then you end up with situations like this. So again, through these interactions, by the braking that they take, you start to see these emergent phenomena, in this case, traffic jams, in the other case, crashes in the market. Or even things like this. Does anybody know what this is? What type of bird? I don't think you get them in Singapore, but in Europe we get them. These are starlings, and probably you've seen these pictures before. So these are murmurations where the birds are flocking together, and you get these kind of beautiful kind of emergent forms that are happening. So these are all different types of complex systems, but you'll find them, like I said, everywhere. The brain is considered a complex system. Things like the immune system are considered complex systems. So why are these things important? Well, the challenges and complexity, and particularly for policy questions, are they exhibit a range of phenomena that make it hard to understand the question of cause and effect. So what is causing the flock to happen? The question of what causes a crisis, a financial crisis to happen, is very, very hard to track, because all of these things interacting together lead to the outcome. And you'll find there's a great paper by a guy called James Ladyman, where you'll find different descriptions of these different phenomena that complex systems exhibit. So things like feedback loops, so where one person or one bird takes an action, that creates the perception of another bird to change its behavior, and you get these continual kind of interactions. You also get nonlinear responses. So a nonlinear response means that for, let's say, one trade can actually just tip the system, or a small trade can create a very, very large response, whereas before it's not created this large response. This emergence, path dependence just means the order of things matter. Self-organization, these systems can self-organize and they can adapt and learn. And there's many other things that happen in these complex systems. So the question then is, how does it relate to social systems and policy in particular? Well, what I've shown here is one, well, first of all, are there any sociologists in the room, trained sociologists? No, maybe there are online. So I hope I don't offend anyone by saying this, but if I summarize sociology in one sentence, it's largely involved with reasoning about collections of individual behavior and how those individual behavior relate to group level phenomena or macro level phenomena. So I use those terminology probably throughout the talk. So the micro is, in this case, how people are choosing to buy their house. So they're looking at the neighborhood, they're looking at maybe the nearby schools, they're looking at the price, obviously, and where their friends are. And then through these interactions, you end up with situations on the right. So this is a map of a US city. I don't know if anyone of you know where it is. There's a famous road in the middle that divides the city. So this is Detroit. And what you see on the middle is the 8 Mile. You see the African-American and white American completely segregated. So the question is, how does these individual behaviors lead to these responses? And then coupled to that is, okay, what kind of control can policy have on that? So there's a great book, if you're interested, called The Color of Law, and it describes how US policy over the last half a century has actually exacerbated the segregation in the US. The other problem with these complex systems is once you get the system into a particular state, it can often be very, very hard to get them out of that state. So by already putting the law in place to, let's say, encourage segregation, you make it hard to reverse this. Once you're in this state, you need a lot more energy in the system to do it. And another characteristic, all these characteristics, it's very hard for these policymakers to reason beforehand the effect of what they're going to do, because you get all these feedback loops, because you get this adaptation. Once you put a rule in place, regulation inside the financial sector, the traders are going to adapt their behavior and do something that you didn't expect. So they really are faced with this really difficult problem. And there are there are few things to really say or to reason about how these policies might be used, or how to design a policy. So fundamentally, what I do, and a lot of people in my group, and also in the Institute for Advanced Study, we consider these social processes as algorithmic phenomena. So that means these agents, if you like, these individuals in the system are following sets of rules one by one, and then they're changing their environment which they're operating in, and then changing their behavior. So you buy a house. By buying that house, you might increase the house price in that neighborhood. That means the next person's got to pay more, and that can then reinforce to become a segregated neighborhood in terms of income. By the way, does anyone know what this video is of? Have you ever heard of Game of Life? This is a 3D visualization of the Game of Life. So one way to kind of reason about algorithmic phenomena is something called agent-based models. And that's where a lot of my research is focused. And these agent-based models, you basically describe the system as a computational representation or virtual representation of the real system, and you're modeling every individual in that system. And then you're giving the virtual agents rules for their behavior. So what I show here is a very famous agent-based model, which you can have a look at afterwards, which is called Boyd's, which is saying birds in a New York accent. And you can recreate those same starting flocks or those murmurations with three very simple rules. Each bird looks at its local neighborhood. It tries to get away from anything that's too close. It tries to align with its local neighborhoods to steer in the same direction, and it moves closer if it gets too far away. So with those three very simple rules, you actually can then recreate those murmurations. The interesting thing is that one of the first examples of this that you probably have seen is in the Lion King movie. So in 1989, there was the first Lion King. There's a scene where the wildebeest cross the hill. That's actually modeled with this system. And it's also now kind of the biologically accepted way in which bird flocking is happening. Also, some people think that the fish schooling is the same way. So this is the idea of the agent-based model. So I want to talk a little bit about what I consider the first agent-based model, which is by an economist, actually looking at the question of segregation, in particular, the question of segregation in Detroit. So Detroit, the picture that I showed, around the late 60s, early 70s, they had this problem of what they called white flight. So this was the white people were moving from certain neighborhoods to other neighborhoods and staying together. This coincided with the collapse of the car industry in Detroit. And Schelling, he actually won the Nobel Prize for some of his work. He did the first non-computerized agent-based model. So he was sat on a plane with a checkers board or a drafts board with white and black pieces. So there was a grid, and he made a simple rule that any white checker or white draft would look at its neighborhood, which is the 8 nearest neighbors. If there's too many of a different type, they would move, right? So the rule was just described as below. You look at the total number of neighbors, n, and you look at the number of different neighbors, nd. As long as that's less than some alpha, I'm happy. If it gets bigger than alpha, then I move to another neighborhood where I might be happy. So the question is, what level of alpha do you need in order to get segregation? So the first thing he assumed was that this alpha should be reasonably high. It should require a certain amount of level of preference to cause a system to segregate. And then he did this by hand. We won't do it by hand. We'll do it on a simulation. And he looked at different levels of alpha. So what you see from left to right is on the left is 0.7, which means I'm happy as long as at least 70% of my neighbors are the same as me. So in this case, we've got the blue and the yellows. And what you see on the screen are crosses. If there's a cross there, that means they're unhappy. So they're about to move in the next step. So at every iteration, each agent looks at its neighborhood. If it's unhappy, it moves to one of the empty squares. And this just continually evolves. So at 70%, you would expect, probably you would get some segregation, right? You want the majority of your neighbors to be the same as you. So if we run that, then you see what happens. You start to see the same pattern. The pattern is completely random, depending on the initial, well, not completely random, but depending on the initial conditions. But you see something happening which looks a bit like Detroit, right? Complete separation. Actually, when you run this, the alpha that comes out at the end, on most neighbors, on average, have 98% the same. So 98% of the neighbors are the same. And in this case, I tried to keep running it, but still 2.7% of the population is unhappy. I can't make everyone happy here. And then you go to 0.5, right? So this means I'm happy as long as at least half my neighbors are the same as me. So I often ask this question is, what level do you think is intolerance, right? In Europe, people typically say anything above 0% is intolerant, which is not realistic, right? You want to have some familiarity around you, but at 0.5, you run the same thing. It's not quite as segregated, but you still see a high level of segregation. And again, if you look at the final value, all the neighbors end up with 86% the same. So even though they only want 50%, they end up with 86%. And then the surprising thing was that if you could now go down to 0.3, so that says as long as at least 30% are the same as me. So I will tolerate 70% different neighbors. Even at this level, you get segregation. And you end up with 77% of people having the same group around them. So what this tells you about things like segregation, and also about school segregation, even small preferences for your own group can drive the system to be segregated. And actually, I'll talk about in a minute, and I'll explain this a little bit now. In the case of the Netherlands, I work with sociologists. They've done surveys with parents. They don't want a completely homogeneous school. They don't want an all Dutch school. They want their children to be exposed to different cultures. But because of this process, it's almost impossible to find a school which is actually not segregated. So this probably, explains that, the problem is hard. Thinking about policy is hard, but these kind of simulations give you ways to think about it. So I'll now go on to talk about what we call the COMPASS project. So computational modeling of primary school segregation. So this is with myself. Eric is a PhD student. We have a postdoc who's starting now. Willem Boterman, he's a sociologist, or I should say urban geographer in the Netherlands, who I would say is the leading expert in the Netherlands on school segregation. Now, school segregation is particularly hard because the context of the country really matters. The way schools are allocated in the Netherlands is quite specific. The way it happens in Singapore is also quite specific, and the way it happens in my home country of the UK is also quite specific. And these often have archaic rules that were around from centuries ago, which are now affecting this whole process. So you really need someone who's an expert. Andreas Flacker is also a computational sociologist at the University of Groningen, who's working on the project with us. And we're actually financed directly by the City of Amsterdam and the Inspectorate for Schools. So the Inspectorate for Schools in the Netherlands, one of their responsibilities is to look at and measure things like segregation. So what I will talk about, so I'll explain a little bit about what we mean by school segregation. I'll then explain the model that we've developed. Already the Schelling model that I've shown you gives you some introduction to that. And then I've got 3 findings which I can tell you about. I'll explain briefly or summarize briefly how these models were implemented. I'll refer you to some papers if you want the details, but I want to explain some of the findings that we've actually discovered. And also explain a little bit about how policymakers really use these models, right? So computational models, I would say any kind of computational technique, AI, computer-assisted reasoning, let's say, a lot of the attraction to policymakers is to give me an answer. So I just give you the data, and then the expert should say, do this or do that. I'm actually completely against that. I can tell you some horror stories about how that fails. One of the things I want the model to do is actually give them a way to think about the problem and understand the problem. So this model that I showed you for Schelling is not a predictive model. It's a way to reason about the system. And now you understand that even in a simple case with these slight preferences, you will get segregation. Okay, and let's see how much time I have if I can get through everything. And then I've got some conclusions at the end about what we're doing in Amsterdam. Okay, so school segregation. It's as you expect, so the degree to which 2 or more groups of people with particular characteristics, and this could be ethnicity, it could be gender, it could be income, it could be education, social class, ability, how they attend separate schools. And what we're talking about in school segregation at the beginning of this talk is I look at school A and school B, what's the population of each group in those schools? What I'm not looking at initially is the segregation within a classroom. So one of the questions that people talk about and ask about school segregation is, why does it matter? So surprisingly, some of the teachers, well, it's not surprisingly, but some of the teachers actually prefer a homogeneous classroom. Because if the teacher is of the same ethnicity, the same background as the students, it's often easier to teach. If you have a very diverse group, it can be harder to teach. So there's an incentive for the teachers to keep those classrooms homogeneous. The biggest problem really, well, there's 2 big problems. One is the social impact of this down the line. So particularly in the Netherlands, there are 2 large or 3 large immigrant communities, Morocco, Turkish, and what's the other one? The ex-colony, I'm just drawing a blank. it will come back to me. So one of the Dutch colonies actually traded with the British 200 years ago, Suriname. So Suriname was a colony of the Dutch, and there was a huge group of Surinamese that moved to Amsterdam in particular at one period. So there were four, let's say, major ethnic groups, and you do hear stories about these children going all the way through primary school, high school, being a Suriname student, never meeting one Dutch person all the way through school, which is kind of shocking, right? So if those schools are of different quality, let's say for some reason, then there is certainly a bias. They don't have a fair chance. So it's about social cohesion in the long run, that people should get to meet together and integrate, and it's about equality and the equality of a fair opportunity. So these are some of the studies that we do. So we work with the Dutch Inspectorate. They produce this report. This is in Dutch, but I can probably, my Dutch is enough to explain what this means. So here you can measure segregation across different kind of categories. One is on income. So how are the highest and lowest income segregated in terms of schools? This is education level, so the lowest and highest education levels. This is the migration background. So this is so Dutch and not Western. So this is all the other non-Western groups and Western groups kind of compared. And these are, what you're seeing is over time and for the big cities in the Netherlands. So what you'll see is, well, here on the left, you see something called Standard Dissimilarity Index, which is one of the thousands of measures of segregation, which is another whole problem which I won't talk about. But I won't explain what this is, but just assume this is a measure of segregation. What you see over time is actually, for some of the cities, it's kind of stable. For this is ethnic segregation, this is actually decreasing. So that's a good sign that this is decreasing. But in other places, things like income segregation is getting worse. So you see this actually now with a lot of non-white expats coming to the Netherlands as well. The ethnic segregation starts to decrease, but the income segregation will start to increase. So I think I explained this as well, that parents want a socially diverse school. They want a diverse school in different ways. What Willem, my colleague, found is that ideally they would like the school to contain around 70% of the same group. So that's the same, let's say, educational background, the same ethnic background, and the same income background. And if it gets more than that, they actually start to not like the school as much. So is it just a Dutch problem? Well, no. These are the major OECD countries, and this is again for income segregation for schools. And you see it's high everywhere. I had a look for Singapore. Now, Singapore is a very particular case because of the HDB regulations and laws. But there's two papers. I had a quick look at them, and these two papers, if anyone's interested, I would definitely recommend to have a read. It's showing that in some cases, you do get educational and income segregation in schools. So there are certain neighborhood schools that are dominated by, let's say, lower middle income children, and there are certain schools which are only exclusively high income children. This also has its own problems, right? Okay, so again, you can look at the process of school segregation. What it boils down to is this relation between the individual and the macro scale phenomena. So the segregation pattern are the macro scale phenomena that you're interested in. What drives that are the individual choices of parents, right? Or households, let's say. There's been decades of literature on how or what things parents consider, right? So distance to the school obviously matters. You don't want to travel too far. The composition in terms of everything that we just talked about, there are certain school profiles and things like parental social networks also play a role. So word of mouth. If your friend is going to a particular school and you ask them, okay, is this school good? Then that can affect things. And then things like school quality, if that's reported by the government. So I want to preface what I'm going to talk about now with all of these things. You can think about everything that's there. But what I do, or what we do with these theoretical models, or these agent-based models, is we reduce it to the simplest description that we possibly can. So I will now go through the basics of our let's say, most simple model. There are two processes. We don't couple these processes together at the moment. So obviously, the way you pick your house, sometimes the schools nearby will influence that. And by a school becoming popular with a particular demographic in terms of income, that can drive the house price up. So you get a very complicated interaction between these two processes. But we have to start somewhere. So at the moment, we decouple that interaction. We run a residential choice first, and then we run a school choice. And in the simplest version of the model, we have this kind of simple neighborhood. And what you see is there's these local neighborhoods, which are in the white boxes. At the center of every neighborhood is a yellow circle, which is the school. And then the rest is like the Schelling model, that the neighborhoods, the red and blue neighborhoods can move around, right? We can make more than red and blue if we want. We can make 4 groups, 5 groups, and so on. The only other thing that I want to mention that's important because of various things is we have these green and yellow boxes. And we define these as 2 neighborhoods. Now, this doesn't really apply, I think, in Singapore, but in the Netherlands and the UK, it does. So you can think about your neighborhood in 2 ways. One is your immediate neighborhood, your street. So in some cases, people are really going to streets and counting the number of headscarves or the number of non-white people and deciding if they want to live there, right? So that's really what you see day to day. The other one, which we call the bounded neighborhood, that's more like a district. So I don't know what you would have. I mean, like Ang Mo Kio would be a district, right? That's a big one, or Yishun, or these. Sometimes they develop a reputation. I think Yishun now has a reputation, right? It didn't when I lived here, but it has a reputation. And that immediately can change the preference to live there. So even though your house, your street might be perfect, living in that bad neighborhood can have an effect. And then we can control, the influence of your larger neighborhood or your immediate neighborhood on the residential choice. And we have one parameter, B here. That's actually very important in the Netherlands because, and in particular in Amsterdam, because there is particular areas which are known for the last 30, 40, 50 years to be of a particular type. Okay, so then the residential choice is more or less the same as before. The only thing that really matters is the composition. So again, we've got the red and blue groups. The red and blue group could mean ethnicity. It could mean high income, low income. It could mean education level. It's just 2 groups at the moment. And then the utility that I get from a particular housing slot or a particular location is just the composition of my neighborhood. But the composition of my immediate neighborhood, the yellow one, and the composition of the green neighborhood in some combination. So if my greater neighborhood, like Ang Mo Kio, if it's mainly my group, and my immediate neighborhood is mainly my group, I will be having a high utility if I want to have a neighborhood which is the same as my group. So then what we do is, instead of the simple threshold model of the Schelling model, we look at a single peak utility value. If you've done anything in economics, you'll know what these are, but I'll explain it briefly. So the idea is, like I said, that a particular parent might say, ideally, I would like 70% the same group. I'm only 80% happy if it's 100% the same group. So what you see on the x-axis here at 0 is 0 of my own group. At 1 is completely my own group. So in this case, and on the left, on the y-axis, you see the utility. So this person is most happy, has the most utility, when the neighborhood is 70% the same as them. And then they get this decrease if it gets too homogeneous. So completely homogeneous, if it's all my own group, I only have a utility of 0.8. So there are 2 parameters which govern this TI, which is the ideal point, and the M, which is this discount for homogeneity. Right? So you can do variations of this. So something like this. This is like the Schelling model. I'm completely happy if at least 60% of the same group. And then if it's completely homogeneous, I don't care. Or I can have something like this. I want 50% the same group, and whether it's completely homogeneous or completely my own group or completely the other group, I'm equally unhappy. So this gives us a lot of flexibility to look at different types of households and different preferences, right? So in the model, I can put in thousands of agents that look like this, thousands of agents that look like something else, and I can make all sorts of combinations of this. Okay, and then the school choice in the initial model is pretty simple. The school is picked in 2 ways, or there's 2 things that affect it. One is the composition of the school, right? So households send their children to the school, and that child has the same demographics as the parents, let's say. And then the other thing that plays a role in choosing the school is how far away it is. So just two simple things: the composition, how many of my own group are there, and the distance to that school. And I can control the importance of each of those things by a parameter alpha. If alpha is 1, then only the composition matters. If alpha is 0, then only the distance matters. So if you put alpha at 0, then you're only going to pick the closest school, and then composition doesn't matter. Okay, so when you put all this together, we then have a model that looks like this, and we can do various different experiments. There's lots more things here. What you see on the top right actually is now we've extended this to real data. So from the theoretical model to a real scenario in Amsterdam. We work with the Central Bureau for Statistics, which is the largest collection of its kind in the world, actually, of a database about individuals in the country. So we know everything about their income level, their ethnicity, where they live, where the kids go to school, and so on. So that's a model. Now I want to talk about one paper. How much time are we on? Half an hour. So the first thing that we kind of looked at with this theoretical model was this question of, well, let me explain. The policy question is this. So what you see here is real data, and all these kind of strange names that you see on the right are different cities in the Netherlands. On the x-axis and the y-axis, you see residential segregation and school segregation. So if residential segregation was exactly the same as school segregation, what you would see is them all lying on this y equals x line, right? That means school segregation and residential segregation in that city are the same. And what you notice is that for most of the cities, school segregation is systematically higher. So school segregation is, for 90% of all cities in the Netherlands, is higher than the residential segregation. So the question to the inspectorate from the government was, what are you guys doing? Why is this happening? There's obviously something that you're not doing right, which is causing this to happen. So we tried to understand why this might be happening. And so the question is, what causes this? One of the ongoing kind of theories in, let's say, social education is that people are a bit more tolerant for their house than they are for their children. So they might move to a neighborhood which is kind of mixed, but when it comes to their children, they want a school which is high income. They want a school which is high education level because it's their kids, right? So what they call this is an asymmetric preference for residential and schools. And like I said, there is evidence suggesting Dutch parents find it desirable for their children to attend diverse schools, but making substantial segregation actually undesirable. So the question is, what is going on? So what we could do with our model is we could now put all of these ideas into a simulation. We could say, okay, what would happen if we put exactly the same composition preference, right? This TI, this ideal point, we make it exactly the same for all parents, for their residential and for their school. What actually would you see happen? The other thing that we can do with the computer models, we can just try thousands and thousands of different combinations. So there's a technique, I don't know, maybe some of you know it, called sensitivity analysis, where you can actually vary all the parameters of this model and explore the whole parameter space. It's a huge amount of computation. It takes weeks and weeks to run, but you try everything. And then with these sensitivity analysis methods, you can actually look for correlations in these parameters to see, okay, if one goes up and one goes up, maybe you get a nonlinear response. And what we showed in this paper, this thing is summarizing basically a lot of runs of the sensitivity analysis. You'll find in the top left plot this optimal fraction. Remember this TI. This is your ideal composition, right? 70%, 50%, 60%. So remember I said that the parents in the Netherlands, they actually want a 70% composition, ideally. What you see here is the orange, green, and blue lines. So the orange line is the school segregation, the blue line is the residential segregation, and the green is the increase in school segregation. And around this 60% level, so if you have a preference for 60%, you actually see the biggest difference, the biggest increase of school segregation versus residential segregation. So what you're seeing in the Netherlands is actually just a consequence of their slight tolerance. So what's happening is they have a 60% preference for their neighborhood. they pick a house, and then they have a 60% preference for their schools, and then you get this double selection process. So the same thing that you saw with the Schelling model now is happening twice, once with a residential and once with the school. So it's natural that you get a higher segregation level. So what the model actually shows here is you don't need this asymmetric preference. It doesn't prove that this is the way it does it, but you don't need the asymmetric preference to get this increase in school segregation. What it also shows is actually around this 60% level is where you'd expect the maximum increase, which is kind of, when you think about it, it's kind of intuitive. If you had no preference whatsoever, you get zero segregation in the neighborhood and in the school. If you were completely intolerant and you wanted a completely segregated neighborhood, you would not get any increase in the school segregation because you're already fully segregated. If you think back to that picture of Detroit, which is completely segregated residentially, there's going to be no schools that have a mix because the whole neighborhood is completely dominated. So this was kind of, let's say, reassuring to the school inspector that it's not something that they're doing wrong. It's just a natural consequence of the system. And again, this is one way in which these models can be used to help policymakers realize that, what are the limits of what they can do? What is a normal behavior? Is this what you'd expect to see? Yeah, this is just the same thing that you can show for different utility at homogeneity. Remember, this is the discount, and this is also affecting things. So if you have a very, very strong peak and you really don't like homogeneity, you will get, again, different behavior. The other thing that's interesting about these kind of results that you show from the theoretical model is the sociologists that I work with now can go back and do new studies, new questionnaires with parents to ask new questions. Because it's a case of, how important is distance, how much is preference, how much do you actually discount when you're in a homogeneous school? These things are normally just not asked. But by doing that, you can then start to have this interplay between the surveys, the qualitative data, and the model. And then you can rerun these things again and again. So if you're interested in a bit more to find out the details of this, I can send you the paper. But now I want to go on to something else. I think I still have time. So one of the things that I talked about at the beginning is this question of segregation. One of the things that you hope by making an integrated classroom is that you improve society later on. It's also part of the reason that I think Singapore had this very strict rule about HDBs. By forcing people to interact or having people interact across different groups, ethnic, income, whatever, later on in life, the society should benefit because people are well integrated. So the assumption is that when you make a well-mixed school, that those well-mixed schools should translate into lots of intergroup friendships. So having a 50-50 white-black school, you should expect a lot of mixed race friendships. So what we did with this model is we looked at now inside the classroom. And we use this technique called exponential random graph models, which are, if you've done anything in networks, is a way to generate networks procedurally. I'll try and explain it. It's a little bit involved, but I'll try and explain it. So what you see here is on the bottom left is an equation which describes the utility that I get from establishing a friendship or a connection. So friendships are networks. So if two people have a connection, or if I'm connected to you, that means I consider you my friend. We can have a two-way connection, so you also consider me your friend, and so on. So direct friends, this is just the amount of direct friends that I have. Mutual friends is the number of people that I have a two-way relationship with. And this indirect friends is that I get a benefit if I'm connected to you and you're very popular. So I look at how many connections you have. And then this thing on the right is just the cost. The assumption is that the more friendships that I maintain, the more expensive it is because I have to invest time in those friendships. Now, there's one thing comes from a guy called Angelo Mele. The one thing that we've added to this, which is a little bit different, is this term Hij. Hij just represents the homophily. So I don't know if you all know what homophily means, but I'll explain it briefly. So homophily is just a distance metric to say how different we are in social terms. So the homophily might measure things like income, ethnicity, cultural background, education level. And if you're from a very high education and very low education, we would have a big distance in homophily. And then you can make this a vector, which is this xi here. And the more things that we have which are the same, the closer we are socially. And the idea is that I get more utility or lower cost if I'm with someone who's very similar to me. It's just easier to maintain friends who are very similar to me. that's the assumption about the model, right? There is obviously evidence for this as well. So then I need to check what I have on the next slide. So let me explain this a little bit first. So the way the model works then is we just throw the group of school children in the classroom, virtual classroom, and we let them evolve this network over time. And they're randomly removing and adding edges to see if their utility improves. So they're maximizing their utility based on this, this equation. And again, based on this homophily. I can make all sorts of different classrooms. I can then also play with the effect of this homophily. So these are standard equations, but depending on how far I get the distance in terms of the vectors, I can get a nonlinear effect. So it could just be a linear decrease, or it could be a sudden shock that, okay, as long as we have two things in common, we're totally happy. But when we get three things in common, it's nothing. So I can vary this and play with these. So we did this with data used from what's called the Ad Health study. We actually were doing this in the Netherlands with a group of sociologists. They were doing the same kind of survey, which I'll tell in a minute, but because of COVID, the whole thing stopped, which is a big pain. But in this study, what they did is they went to the school and they asked the children to name 5 male and female friends. So who are your closest 5 female male friends? And there was data about those people, right? So the sex, so are they male or female? What race are they? And this is American, so it's white, black, Hispanic, Asian, and then 5, which is mixed other. So that could be all sorts of things. And then what grade were they in? So what level were they in? Then you can see the race. So you see most of the children are white. Second highest group is black. Third Hispanic, and then mixed other is the 4th one. Now, what I will explain a little bit is in network science, there's something called assortativity, which explains how likely you are to find 2 nodes which are similar connected to each other. So the measure of assortativity is also a measure of how segregated the network is. So we can use it as a segregation measure for network. So you'll see that when in the grade, people maintain their friends only in their same level, which makes sense, right? Also, you'll see sex is actually quite important, but also race is quite important. This is for high schools. If you take this to primary schools where we work, sex is the #1 thing. Boys don't play with girls and girls don't play with boys, right? So what we did is we took our model, we then calibrated this using actually something that we did, Wentong and I did together, this genetic evolutionary algorithm, and we calibrated the parameters of the model, all of these different weights, as you saw, and then you can see the assortativity measures of the different schools that we used and how well the data agreed. Now, I want to point out a couple of schools here were 53, 54, 78. So you'll see that the observed segregation level is much lower than the one our model predicted. And I'll come back to and explain to why those might be. But maybe you can think about it yourself. What is particular about those schools? Okay, and then what we found, okay, we can validate this. Here we have racial group 1, 2, and 3. These are plots which show for different levels of the 3 mixes, so it's 3 groups, you can measure the assortativity. So in the case of the right-hand side of the top plot, you'll see it, the right hand, it's very hard for me to do online. I don't think my mouse is working. Let me see. If I can, my mouse has disappeared. No. Okay, so the top left plot, the blue line where it says RG1, this actually represents where you have 0 concentration or 0 number of students from race group 3. And here you see when you've got 2 groups, you get maximum assortativity. And then as you get more groups, you get less assortativity. Then you'll see that on the right-hand side, the data and the simulation, and you see this is kind of in fairly good agreement. So the model was, let's say, kind of producing something that we might expect. Now, one thing that we did, one thing that we found from that original result is the schools where we were overestimating segregation, what was happening is those were schools with a mixed race group. So it seems that these mixed race groups are acting like a bridge between the two groups that are there. So which is kind of remarkable. So we also did the same thing here. And what we did is we had this homophily or dissimilarity measure between the two groups. And we said, okay, we made a very simple assumption that these mixed race groups, instead of being a distance of 1, you're now a distance of 0.5. And indeed, what you see is that in this case, race group 3, it has an effect of dampening segregation in the classroom. Now, the other thing I want to say here, which I didn't mention, I should mention, the interesting thing about this result, also from the data that it shows, is that when you have a perfectly mixed school, right? So 0.5 of one group and 0.5 of another group, that's the kind of thing that we're attaining for or trying to obtain in a mixed school. That's actually where you get maximum classroom segregation. So when the school is 50-50 mixed, you look at the classroom, then you're going to see maximum assortativity in the school network. And this makes, if you think about the way the model works, it makes sense, because if you've got a supply of friends in your own group, you can just make enough friends to sustain yourself from that group. And this is also what the real evidence is showing as well. So again, you go back to this assumption that we're making about trying to reduce segregation in schools. If your objective is to create more interracial friendships, this might not be the way to do it. You might then go to say, okay, the best way to do this is then you make more mixed race kids and put those in the schools. But then you get into all sorts of ethical questions, which I don't want to say. But again, this playing with these models, playing with these experiments, it starts to illuminate certain things that you might not have thought about beforehand. And when I show this to the people from the inspectorate, it's obvious when you think about it, or it's at least plausible, let's say, and then they have to kind of reevaluate what they're doing. So I think I'm just in time. So now this is really, as we're speaking, this is being done by my PhD students, so it's really hot off the press. So I may get some things wrong. Let's see. So we've been now looking at the data from Amsterdam. This is a picture of Amsterdam. Amsterdam has this very strange structure, which is cut off in the middle. You see, it's so this part in the bottom right is part of Amsterdam, and you'll see this is based on income. And you'll see the red area. This is an area called Amsterdam South, where it's a very, very wealthy neighborhood. So we've been looking at income, and we've been looking at now not simulating residential segregation patterns, but the real residential segregation patterns, and then looking at how kids are going to school. And we're simulating that, but also looking at real data to see what's going on. Now, one of the questions, one of the problems about Dutch society, which we've discovered, is the way Dutch society operates is they don't use cars. So if you've ever been to the Netherlands, you've ever been to a Dutch city, they don't have big out-of-town supermarkets. They don't have big shopping malls. They have lots of small things, and everyone goes by bike. So it's very normal that you go to school by bike. In fact, I think 80%, 85% of all travel to school is by bike. So you don't have a traffic jam in the car, you have a traffic jam by the bike. What this means is that you need a high density of schools. So there's a lot of schools, primary schools, but they're relatively small. You don't see the Singaporean style, which is 1,500 students. It's about 300, 400 students. And what it means is that when you're living in Amsterdam, you can walk in any direction within a kilometer and you'll have quite a lot of schools to choose from. Now, when you think about what that does, if you only had one school in a city, there's no school segregation. If you have two, it's also harder. So the more choice you actually offer in terms of the number of schools, the easier it is for biases to perpetuate. Now, if the bias is not there, you won't get segregation. But in order to have a bias, to say I have a preference or an intolerance and I want a school which is my own, the more choices you have, the more ability the system has to kind of find that solution, let's say. So that's what we've been looking at. Here you actually see real data. So this is for the two groups. And what we thought is maybe the lower income neighborhoods have less choice and the higher income, it's actually not true. It's just well distributed across the city. And you see on the x-axis, this is the distance. So within X kilometers, how many schools they have to choose from. So at 1, it's already like 5 on average. At 1.5 kilometers, it's already like 8. And within 3 kilometers, which is not very far on the bike, you've got 12, 13 schools to choose from. Now, part of the reason we do this now is Amsterdam is putting in different policies to actually control school choice. So they have a website, which I can dig out for you in a minute, where you put in your postcode, and then you get a list of 8 recommended schools. Now, why 8? That was completely random choice. There was some kind of argument for it, that, and it's the 8 closest, right? And then they put in one, I think, one Islamic school, because if you want to go to, you have to have that choice. And I think one maybe Montessori or some special kind of pedagogical school. Now, if you're not Dutch, you don't realize that actually by Dutch law, you have complete freedom of choice. So no school by law can reject a child. So you have complete freedom, but by nudging the parents in this way, by giving them these options, you're already steering the system. But 8, you already have a lot of choice. What we've been now playing with is looking at the effect of school distance. So in the simple model, right, the closer the school, the more utility you get. But actually, what we're finding from the evidence is school distance is not really a utility, it's more of a cutoff. So what you say is, okay, I'm going to look at all schools within a certain radius. And if it's 1 kilometer or 1.5, it's the same. What I'm more caring about is the actual school composition, the school quality, and things like this. So we're playing with that now. And oh, I think I missed a slide. So I'll try and dig that out. We have some results. I can remember what the result shows, but what we showed is that even with the 4 closest schools, with a preference of 70%, you're going to get school segregation. So even within that scope, the system has enough search space, let's say, enough opportunity to find a solution which is segregated. So the story, or the moral of this story, seems to be that segregation is just really, really hard to prevent if the people have this preference. Okay, so I think I mentioned this already, but I want to re-emphasize it again. So what do policymakers need? It's kind of what if scenarios, right? So one of the questions is now in Amsterdam is they want to close schools because the number of children is decreasing massively. The normal model is you go to university in Amsterdam, you have kids, you leave Amsterdam. So there's an oversupply of like 300 schools. So the question is, they need to close some schools. And what we've shown with some of the simulations, which I didn't mention here, is if you do something sensible, like look at a neighborhood and close the most segregated school, you can actually make the whole system worse. So by closing that most segregated school, you get that group then going to other schools which weren't segregated, and that can tip the preference, tip the composition to now where people see this as a white school or as a black school or something else. So by closing a school, without thinking about it carefully or maybe simulating it beforehand, you might actually make the system worse, even with these simple things. So it's the understanding, it's a prediction, it's playing out the possible set of futures. And I think this is a great book for everyone to read, the Book of Why. And I like to go back to this explanation versus prediction, right? Prediction is the ideal, but I think explanation, reasoning about systems with the computational models is much more useful. And there's this one particular minister that I was working with in the Netherlands who was very, very insightful. He gave this great quote, which says, "I consider a model successful if it is able to tell me what I need to know, and then I can throw it away." So he doesn't want it to do his job for him. He wants it to help him understand things. And then, in case anyone is interested, I just wanted to mention this. So at the Institute for Advanced Study, we have a new center, or a new virtual center, let's say, we call Polder. So Polder is the thing that they build dikes around in the Netherlands. But this is about policy making and decision making. We have a number of projects with all sorts of different ministries now. The City of Amsterdam, the Dutch police, the Inspectorate, Ministry of Economic Affairs, and everything else. And it's all about bringing policymakers together to help build models and help come up with solutions. So with that, I will stop just in time. Thank you very much.
Okay, yeah. Thank you, Mike. Any questions? So those the audience physically participate here. So do you have any questions? Then those that participate online, if you have any question, then you can type in the chat box.
Yeah.
So I guess for your simulations on the first part, you're assuming the same sort of utility function for all agents.
Well, it depends what you mean by the same type of utility. At the moment, it's this single peak utility value.
But with the same values for all agents and all.
So we have in the what I showed, yes, because it was all about this this assumption about asymmetric preference. So in that model, we fixed it, but in principle, it can be changed. So you can make one group different to the other. It's also in these idealized scenarios, we've got 50-50 mix. No immigrants wants a 70% composition of their own type, right? So yeah, it then starts to become relative. So what you can do is say, okay, what is the total composition of, let's say, Turkish people in the Netherlands, and then is that school underrepresenting or overrepresenting that group? But actually, in some of these neighborhoods, they can be completely Turkish schools, so we're really segregated.
Right, so this is one question on the Q&A. So Mike,
Yeah.
If you click on Q&A, then you should be able to see the question.
Yeah, so it's about the ethnic integration program introduced by the HDB. Yeah, so I know it well. I also, because I lived in Singapore, my wife is Singaporean, so I know how this works. I also know a little bit about the history of it. So I think at the time it was very vital for Singapore to have this to make a new country, let's say, a very young country. Do I think it could be useful? Yes. I mean, this is what they call, in sociology, this is called active intervention. So you kind of control the system. Yeah, sorry. You control the system to make sure that segregation can't happen, right? So you enforce it. It's very effective. It's really effective. But in Europe, it just wouldn't, people wouldn't accept it. It's as simple as that, especially when it comes to schools. There is this, in the Dutch law, there is this, there's actually written in the law that you have freedom of school choice. This goes back to the Dutch Reformation with the Catholic and Protestant kind of, so there's a large group of Catholic and Protestant schools in the Netherlands. So they already had this problem, religious segregation, not ethnic segregation, 200 years ago, 300 years ago. So yeah, I think it could definitely work, but it just wouldn't be accepted, I think. Hopefully that answers your question. The one thing that I can mention about that as well. So in the US, in the 70s, they started a program which was kind of similar, which was a bus to school program. So they started shipping kids from poorer or black neighborhoods to schools which were in rich white neighborhoods. And school segregation then kind of, and the idea was to start the system so that they wouldn't be known as white schools or black schools. But as soon as they took those buses away, segregation went back to exactly what it was. So, yeah, I mean, the only other thing I can say here is that, you know, I've given this impression that maybe I get this impression that the residential segregation, school segregation are largely decoupled. It's actually not the case, right? So residential segregation is always one of the largest causes of school segregation. If you're in a neighborhood which is all one group and there's no other groups in that neighborhood, people are not going to travel from outside, especially if it's a different group.
Yeah, I have a question just to follow up the question just now regarding the utility function. Well, so right, so if I understand your answer, so currently you're only considering homogeneous agents. with some utility. I
Well,
mean, in terms of optimal
in terms of the behavior,
yeah. So what's going to happen? I mean, if you have heterogeneous relations, all with a different utility. I mean, we have a similar result or different result.
It all depends a little bit on this relative fraction. So if this whole thing is completely simplified and stylized, right? So you don't have two groups, you don't have one characteristic, you have all these combinations of characteristics. You could argue that these then boil down to one continuum of, homophily, let's say, but then it becomes a lot grayer. And then you probably will only then see at the extremes, right? So there's going to be certain characteristics like income, which are going to really drive the system apart. And if the utility of this ideal point starts to change, or if the population is really homogeneous, then it's hard to say. It's hard to say. It probably depends on if you've got these highly intolerant people. The question is, what fraction of those highly intolerant people would you need in order to perturb the system to something that you can't control anyway? So probably you only need a small fraction to drive the system to segregation, I would guess.
The other question is, so the currently studies is mainly on primary school.
Yeah.
So do you think this, the result will be similar for secondary school or even for the university?
It's a good question. So there is a little bit of reason to this. So one reason is that, well, primary school typically is when parents move house and they pick a school based on that.
Yeah.
The other reason in the Netherlands, the secondary school system is very strange. So at 11, they take a test and that determines whether they go to university. So at 11, you know whether your child goes to university. So they have something called the VWO and the HAVO. These are like what would be considered a polytechnic and a classical kind of high school education. So in the VWO, they learn things like Latin and Greek and very, very kind of old-fashioned things. In the HAVO, they learn more applied things. That's determined at 11. So what happens at 11 is these kids get a recommendation. And if they go to a primary school, that the recommendation that they get will be one particular VWO, one particular HAVO. So the ability to change very much, change a lot at the high school level is constrained because of this policy. Now they are changing it to have this integrated first 2 years. So when they go to high school, it's mixed, and then they determine that thing there. The other thing is that if you remember this picture of Amsterdam that I showed you, all of those VWO schools in Amsterdam, they're all in Amsterdam South, the posh neighborhood. So what you do see is if kids excel in one of these levels, they can get promoted to, so if they get recommendation here and they do very well, they can get promoted to the higher one. The other way around can happen. If they're in recommended for VWO and they struggle, they can get pulled down. If you look at what happens in terms of ethnicity in those two dynamics, it's completely different. So a lot of the kids from minority backgrounds, they get recommendation to the highest level. They're very talented students. They end up dropping down because they're just totally unhappy, because they have no friends, they have no social circle. So it's really, and of course, the whole thing with COVID has made this a million times worse because of the disparities in home education.
Yeah, in a way, it's quite similar here in Singapore, right? And so the most important exam is the PSLE.
Yeah, but I don't know how much the. I mean, I know there are very, very good schools, and they're dominated by people from high incomes. But I don't know how much your income really influences that. I think the PSLE, in some ways, so in the Netherlands, it's the test, but also the recommendation from the teacher. And of course, there's all sorts of studies to show that these teachers' recommendations are highly biased. If you're in a school which is a minority and the average is very low, they're very reluctant to give this high recommendation. Yeah, so it's dealing with all these different systems. You know, it's not much.
Okay, so I didn't see any more questions on the Q&A in the chat. Does anybody else here? Okay, so I guess that's bring us to the end of this seminar. So let's thank Mike again for a very interesting talk. All right. Okay, also I'd like to thank the audience, as I mean, participate physically or virtually, all right, for attending this talk. Right now it's advertisement for NIS, right? So please follow NIS on social media platforms, Facebook, Instagram, and Twitter to learn more about this talk and to access the research papers, right? And we look forward to you to participating future NIS events, right? So thank you. So that's end of the seminar. Bye.